All right. Chapter 7. Atomic structure and periodicity. One thing you want to focus on for this one is periodic table. Because this table is set up to reflect the atomic structure of each element. And you'll see that as we go, they're in these positions for a good reason. And the structure of the table tells you lots of information about the element once you identify where it is. Okay, first of all, most of what we know about the universe comes to us, the information comes to us through light. Colors of stars tell us what their temperatures are. They call it black body radiation. The hotter it is, the closer, the more blue it is. Red giants are really cool stars, relatively speaking. And white dwarfs are extremely hot. Okay, and there's the gradation in between. Our sun is pretty much yellow, right? And that gives you an idea of what its temperature is. So then the question becomes, why do these colors develop at those temperatures? It has to do with the energy that's imparted to each of the atoms. And the higher the energy that's imparted to the atom, and the energy that it releases as a consequence, is a reflection of its color. Okay, so light, there's been a controversy raging for decades, if not centuries, about the nature of light. We're going to approach it at first where we consider light as a wave. The other possibility is light as a particle. Okay? And what science has decided to do is say it's both. Right? Because each one, depending on what situation you're in and what questions are being asked, can be answered by either this one or that one. You just have to pick the right theory to go with it. So, first of all, light is a wave. Light then is characterized, in fact, all waves are characterized by these three variables. The wavelength we represent by a small lambda, which is the Greek for wavelength. Frequency, which is just a small f, it's not Greek. And then speed or velocity. Right? So those three characterize a wave, and they're all related. So how are they related? Well, in the case of light, well, frequency, there is a Greek letter that goes with that. Even you might see it both ways, is the reason I'm giving it to you. This is the Greek letter nu, N-U. And this is the anglicized version, F for frequency. So in this case, we say we know the speed of light, and it's given a small c as its value. Speed of light is 2.9979, I think. 2.9979 times 10 to the 8 meters per second. And these are SI units, meters per second. So, and that is a constant in a vacuum, of course. And it's not much different than that in air. Right? So we can use it for situations where light is traveling through the air. But this value, being a constant, is related to these two, and of course this one is C for light, is related to these two in this form. The wavelength times the frequency is the speed of light. Now we can check ourselves, right? This is going to be meters per second, units. Wavelength is going to be in meters. And frequency is going to be in hertz. The hertz is also equal to reciprocal seconds, which is 1 over seconds. So many waves pass a fixed point in a second.
So that's the frequency.
This is frequency, which you'll see it as hertz, but if you're going to do any calculations with it, you need to use reciprocal seconds. In other words, 1 over seconds. And this 1 is number of waves, right? Number of waves per second passing a fixed point. So if we know one of these, we can find the other one because this one's fixed. Okay. So this is a representation of waves, right? You've all seen waves on a pond. You see peaks and troughs, right? And the distance between a peak, one peak to the next peak, right, is the wavelength of that wave. And if we fix our gaze right here, right, and count the number of waves passing that point in a fixed amount of time, and we prorate it to seconds, then we can calculate frequency. So if your frequency is 4 hertz, we should expect 4 of these waves to be traversed in 1 second. Right? That's the case there. And 1 second is given that distance for each one of these. There are more waves, and there are 8 of them in this one 1 second, and there are 16 of them in this 1 second. Okay? So the characteristic of a wave. Let's see. All right. So now that we've characterized light as a wave, that's where the colors come from.
I remember one of this like this.
Good. It'll come back to you. This is the electromagnetic spectrum. These are all of the light waves that we've been able to identify. Gamma rays are the shortest wavelength, right? 10 to the minus 12 meters on this scale's wavelength. And this, well, we don't have frequency here, but notice that the relationship here, the product equal a constant, is an inverse relationship. So as the frequency gets smaller, the wavelength gets bigger. Or if the wavelength gets really, really small, this one has to be big. Okay, so they're inverse relationship. And as it turns out, the part of the spectrum that we can see is very narrow. It's just a little sliver. Okay. So we can see well, if you've been introduced to this topic before, you know the acronym for the visible wave. Start at this end. It's Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. I got kind of wishy-washy down here. Blue, violet, yeah, but where's indigo? It's in there somewhere. Okay. But as you go from red to blue, violet actually, the wavelength decreases. It goes from 7 times 10 to the minus 7 to 4 times 10 to the minus 7. So that's really a narrow range because you're still the same order of magnitude. Right? So if we say, and here's another way that you may see it, 7 times 10 to the minus Better throw that one away. Let's try brown. That's 7. If this is in meters, you may also see it sometimes in nanometers. So it's a nanometer is 10 to the minus 9th meters. So if we convert this to nanometers, right? So 10 to the minus 9th meters is 1 nanometer. So if you divide that into this, that becomes positive on top, so you have 100 times this one, and that's 700 nanometers. Okay. Now, if you want to go the other direction, say you're in a problem, you're given nanometers as the wavelength of your light. Say it's actually it's more like well, let's take one in the middle. Let's just take 550. Yeah.
You said that's 700? Then that's fine. Well, I got 70 for that.
All right. This becomes 10 to the plus 9th, right? It comes up here.
I probably did something wrong.
Yep. So that's plus 9 minus 7 is 10 squared, which is 100 times 7. So if you want to convert that to meters, which you would have to do for some calculations, particularly where that unit of meters, then what I do is just say 550 nanometers is just take this nano part and put it out here, 10 to the minus 9. So it's 550 times 10 to the minus 9 meters. Just take the value of that nano and put it out here, and then you reestablish scientific notation, which would be 550, 5.5 times 10 to the minus 7 meters. Okay? So you can do those conversions on the fly.
So you're trying, like, so basically you're just bringing meters and nanometers?
And go back and forth.
Okay.
Right. This is using my traditional unit conversion. And this is going and taking that nano part and just putting it out here, 10 to the minus 9th is a nano. Leave the meters. Right? So it's 550 times 10 to the minus 9th meters. And then you just convert to scientific notation. Or if you're doing a calculation, why bother, right? 550 times 10 to the minus 9th meters. Punch that in your calculator. Right? It's accurate. Your calculator is going to do the rest for you. That's only if the answer is called for in meters. Then you need to make the conversion. Okay, so the visible range of the spectrum is very narrow. And the shorter wavelengths are off the end of the violet side, ultraviolet, right? So these are the ones that give you sunburns. X-rays are the ones that tell if your bone's broken. Or if you got a cavity, don't want to leave the dentist out. And gamma rays are just extremely high energy, and we usually only produce gamma rays on the Earth surface with an atomic blast. Most of the things don't have enough energy to produce them. So the rest of them come from space. Right? You've heard of gamma ray bursts. Talk about those, how dangerous they are. They come from, well, there's various theories, but from wherever they come, they're very directional. So if a gamma ray burst is aimed directly at the Earth, we're in trouble. Right? The other side, off the red end, is the infrared. So the wavelengths are getting longer. That means the frequencies are getting shorter. So infrared, that's what keeps your French fries warm. those red lamps. Microwaves, that's what cooks your meals, you know, if you're lazy enough to use a microwave. And then the radio waves are what we primarily use for communication and radar ranging and that type of thing. Okay. So, why are we showing that pickle? I think that's a pickle with some direct current going through it. The point of this slide is that the reason it's glowing is there's energy being dumped into that pickle by way of a battery and direct current. And the reason we know there's energy there is because there's light being given off. Right? Remember, energy cannot be created or destroyed. It can only be converted. So when we dump energy into that pickle, it's going to do one of two things. It's going to show us it's there with the light, and or it's going to get hot. Okay, it's probably doing both. You don't want to touch it right now.
Cooking a pickle.
Cooking a pickle, right? Direct current.
Isn't that how like data pumps are kind of?
Similar. When you, like in a microwave?
Not sure. I mean, I've seen where like certain science fairs or stuff like that. As children, you take a potato and power a clock with a potato.
And do the power a clock? That's making a battery out of a potato.
Oh.
That's a different story. Here we're adding energy to the pickle. There you're extracting energy from the potato. Actually, you're not extracting energy from the potato. They probably stick two different metals into it. And the potato just acts as a electrolyte to complete the battery. The real chemistry goes on at the metals. You might stick copper in one end and zinc in the other. Question? No? Okay. All right. So, now what we're going to talk about is, we've alluded to it so far, talking about the energy that's being dumped into that pickle. It can be quantified, right? So the energy that's coming out of the pickle, or a light beam that's traveling from this point to that point, carries with it a certain amount of energy. And the energy that it carries is proportional to the frequency. So the higher the frequency, the more energy it has. Right? So the gamma rays, having very short wavelength and very large frequency, are the most energetic. They have the most energy. And of course, if this is proportional to that, there's always got to be a proportionality constant. So we designate that with an H, and H stands for Planck's constant. Named after Max Planck, who did research on this stuff. So all we have to know is Planck's constant and the frequency in hertz, right? Cycles per second. And we can calculate the energy. And if we use Planck's constant, the energy is going to be in joules. Just like our calorimeters, energy is in joules. Like our delta H's or enthalpies in joules. Right? So the constant is chosen in its units so that it will produce, by multiplying by hertz, joules. So I guess if this one is reciprocal seconds, then this one would have to be joules seconds. In order for the seconds to cancel, leave us with joules. That would be the units of measure for Planck's constant. You don't have to memorize the value. It's going to be in your, check your review document, the last page. There should be H equals something. Now,
what we're saying here is we're not talking about, well, we're actually bridging the gap. Right? This bridges from light waves we've found to be frequency, but the energy that we're describing is assigned to a packet of light. Right? We call it the quantum. So that quantum of light has this much energy. And that's describing light as a particle.
Quantum is describing it as a particle?
As a particle, yes. And that's why we say energy is quantized. In other words, it has a definite amount. In other words, it's not a continuum. Light as a wave is a continuum.
As a particle.
As a particle, it's discrete amounts. That's the quantum. So we say energy is quantized in light. It's also quantized in atoms, but we haven't got there yet. So this quantum, we give the name photon, right? So that's where Star Trek is the photon torpedo.
Watch Star Trek so much.
Yeah.
Man watches Star Trek.
I'd really like to have a tricorder and simplify lab work a whole lot. And while I'm at it, I put in an order for a transporter. Okay, so energy is equal to h nu, right? Planck's constant times the frequency. But we know that this relationship is true. So if we solve for this one, we have that divided by that. And if we plug this one in over here, we have this one, oops, okay, H. We have this one over this one. Okay? So we have another formula that we can use. If you're not given the frequency where you can use this formula, then you plug the wavelength in as meters and the speed of light times Planck's constant. You get energy also. Okay. Oh, there's Planck's constant. See? Joule seconds. 10 to the minus 34. Yeah.
Why is Planck's constant also with the speed of light? See?
Right here?
Yes.
That's just the way the math works out. That's algebra. We substituted this one right here, right there. So that's where it is. This is equal to that. This is in the numerator.
I see that. I see the substitution.
This is in the numerator. That's in the numerator. Same thing. That was crapping out on me too. Let's see if green works. Okay.
Photoelectric effect, the ejection of electrons from a surface when light of sufficient frequency shines on it. Photoelectric effect is the ejection of electrons from a surface when light of sufficient frequency shines on it. For example, when red light is directed at a metal surface, no electrons are ejected. However, when blue light, which has a higher frequency, is directed at the metal surface, electrons are ejected and a current flows through the wire as measured by the ammeter.
Okay. So what was that all about? The photoelectric effect. We're starting to, with the photoelectric effect, we observe the relationship between quantized energy in light, independent light, just whatever, describe the light, and its relationship to atoms. So if you have a certain amount of energy that's available from a photon, it will kick off an electron. which means the electron that's in the outermost shell then will be given enough energy, like that's why we write energy, H nu, enough energy to be completely released from that atom. So one photon with sufficient energy, right? The red light doesn't have enough energy, right? So that electron's going to stay put. But if you give it enough energy to go to infinity, right? Infinity is the way we describe an electron that it's completely removed from the atom. Then you see the photoelectric effect. Now it's fairly simple to describe like that, but it apparently was difficult to prove mathematically. It took a genius to do it. Got a Nobel Prize for doing it. His name was Albert Einstein. Everybody associates relativity with Albert Einstein or equals mc squared and that kind of stuff. He got his first Nobel Prize by proving this effect, photoelectric effect. He wasn't attached to any university either. He was reviewing patents in a Swiss patent office and did this in spare time. Okay. So we're starting to draw relationships between atoms and light. Oops, gotta retake control. Here we go. Okay, so Einstein did come up with this one, E equals mc squared. And all we're saying is that the energy of any particle, whatever mass, can be calculated if we use the constant speed of light as one of the terms. So mass and energy theoretically are interchangeable. So that's probably where the transporter idea came in. You just convert your person to energy, send them on a beam somewhere, and then reconstitute them on the other side. Of course, the real problem is information. You know, energy is energy. How do we know my energy is different than your energy? Right? So you've got to send, along with that carrier wave, you've got to send information enough to reconstitute my energy into me. And just hope that you don't energize a fly at the same time. Then you end up with a combination. Messy. Okay. So this also emphasizes the dual nature of light. Electromagnetic radiation is a wave, and it's also as a particle. Now, this can also be used. This is if the entire mass of a particle is converted into energy. If, however, you take something moving at a certain speed, particularly if it's approaching the speed of light, then the energy of that particle, or the mass, is equal to whatever its mass is times its velocity squared. Right? So it doesn't have to be going the speed of light. But if it's not going the speed of light, it'll have less energy than if it were traveling at the speed of light. Okay. And that's one of the reasons that the electron microscope works. Light has it has a diffraction limit. In other words, visible light is only good down to a certain size particle, and then you can't see any smaller because the particle is smaller than the wavelength. Okay, but if you use this relationship, you find out how much energy that electron has when you accelerate it at the target. Then, as it bounces off, it produces the wavelength
of a smaller, much shorter wavelength and gives you more detail. Kind of the 50-cent tour of electron microscopy. Okay. So, wait, I don't want that yet. I want to draw a distinction between a continuous spectrum and a line spectrum. Continuous spectrum, I don't know about the girls, but all the boys, I'm sure, had magnifying glasses when they were kids.
At least one.
And you focus the light on an ant and fry it, right?
I use my glasses.
You use your glasses. Okay, that's right. Okay. Well, at that time, I didn't have glasses. I didn't get glasses till I was in the 7th grade. But yeah, they work just fine.
I have used this one side as thick as I have glasses.
Oh, they're progressive. So if you do that, if you actually, it's not the lens, although the lens will give you a spectrum of color because most lenses are not achromatic. But if you use a prism, right, glass or a plastic prism, then you can train the sun's light on a white surface and you see the spectrum spread out. And it's continuous, right? It goes from red to violet with no breaks. That's a continuous spectrum. It contains all the wavelengths of visible light. A line spectrum, on the other hand, is a spectrum composed of discrete lines of light. You may only have maybe a blue or a red, maybe a green. Okay? So that's what got scientists first thinking about the nature of the atom. You know, because if you investigate these, you just take a pure element and put enough energy into it and it glows. And then you take that light and you send it through a spectrometer, actually a spectrograph, and it spreads the light out. And for hydrogen, for instance, you'll only see 4 lines. Right? If you try something else, like, I don't know, helium, you get a different set of lines. So these lines are characteristic of each element. So now we're getting to the point where we can take light from a distant star and find out what elements are there, because we've characterized the line spectrum for each of the elements. All we have to do is see those characteristic lines and we know they came from a particular element. Right? Of course, you always see hydrogen because all stars are primarily hydrogen. But you start picking up other things like helium. In fact, helium was first identified in the sun spectrographically before it was found on Earth. But this line spectrum starts to give us a clue about what's happening in the atom for that light to be emitted only in those characteristic lines. So now we got a little video.
That is passed through a prism separates into a rainbow or continuous spectrum consisting of colors from violet through red.
There you go. A rainbow. Forget the rainbow. Right? Rainbows are continuous spectrum. Sometimes you get more than one bow. Right?
Wasn't a crystal bit?
I'm sorry?
Wasn't a crystal bit? Like
A crystal? Oh yeah, lead crystal. Uh-huh. Right. If you have any lead crystal around the house, you can shine a bright light through it. It won't be a perfect spectrum. It'll be kind of scattered, but you can see the individual colors in there somewhere.
When the light emitted by a hydrogen gas discharge tube is passed through a prism, a line spectrum results. This line spectrum consists of light at only 4 wavelengths in the visible region.
Okay. Now, those 4 wavelengths in the visible region are a clue to the structure of that atom. Now, if we had detectors that were properly calibrated, we could pick up additional lines in the ultraviolet and the infrared.
those regions of the spectrum are used for different types of analysis. But we're not going to dwell on those right now. We're just trying to make the point that the lines in there are due to specific characteristics of each atom. So the first conclusion we can draw from these line spectra is we know that they are due to, since we know that they're at a given wavelength, we can calculate the energy from each one. We know that energy being quantized, these energies, what's the first thing that, well, I've said this before. When atoms approach one another, the first thing they see is their electrons, right? That's where the interaction takes place, the bonds form. That's also the first place that light interacts with electrons. So when light approaches an atom, the energy, if it's the right wavelength, will cause the promotion of an electron from one orbital to the next. Right? So for hydrogen, we've only got that one electron. Right? That's why we're starting with hydrogen, because if you got more than one electron, things get kind of muddy real fast. So we can describe, for this hydrogen atom, the promotion of the electron. If energy comes in of exactly the right amount of energy. So it has to be a certain frequency or a wavelength. So we're discussing here in terms of wavelength. Then that electron will be promoted to the next level. If it's the next quantum higher energy, it'll go up to the next level. Right? Well, the same thing happens if the electron has been excited, say by electric discharge. The electrons have been excited to a certain position out here. Then if they return like that, that energy is released. So it goes both directions. Okay? That's why we can see those line spectra, because in that discharge tube, the hydrogen is first excited, then it gives off its light energy, and we spread it out in a spectrograph, and we see those individual lines. So each line is due to a specific transition of an electron from one orbital to the next. Okay? And there are only 4 of them, 4 transitions that give you visible light. Other transitions give you mostly ultraviolet. Right. Okay. So, why is it significant that the color emitted from the hydrogen emission spectrum is not white? Because it's represented by, it's not going to give us the answer. It's represented by discrete transitions of electrons between orbitals. It's not a mishmash of transitions from lots of different elements. Right? So that would be the case for the sun. There are lots of elements in its photosphere with those transitions, and all those transitions together give us a continuous spectrum. But we can still pick them out, each of the elements. Just like I said, it's this way, but maybe it's not. Okay. It's not meant to confuse, but it's just to explain why we get a continuous spectrum from the sun and a discrete spectrum from hydrogen. Actually, it's probably a physiological artifact. Right? Our eyes tend to blend colors together, like the primary colors. What are they? Red, blue, and green? Red, yellow, blue, green? Red, blue, green. Yeah, red, blue, green. Those primary colors. So we can fool our eyes into thinking that we've got a continuous spectrum when we actually only have a mix of those 3 colors. So I think that's what's happening with the sun. And when you use just a hand prism, it doesn't spread the light far enough for you to see the individual lines. How does the emission spectrum support the idea of quantized energy levels? Well, I just told you. Each quantum of energy, each photon has a certain amount of energy, and it has to match exactly a transition from one level to another to be absorbed, or vice versa. The transition from one level to an inner level, this lower energy is closer to the nucleus. So as you go from high energy to low energy, you give off that energy in the form of light. So I'm going to leave that up there for now. So these, we come to a theory proposed by Niels Bohr. He was a Danish physicist back in the early 20th century. Around the same time as Einstein was busy. They were all buddies and competitors. So his model for the hydrogen atom was based primarily on the solar system. He saw the sun as the nucleus and the planets as the electrons. So he used that as his starting point. And he said the electrons move only in these particular orbitals, nowhere in between. These are what we call allowed orbits or orbitals. And each of these levels or orbitals has an energy assigned to it. And a transition between one or the other is a delta E, a change in energy. And that delta E is converted to light using that formula. Now, the ground state of hydrogen is the lowest possible energy. So the electron has to be in the first orbital, close to the nucleus. That's the ground state, lowest possible energy. Higher energies move out. And we give these numbers, 1, 2, 3, 4. Those orbitals have numbers. Now the ground state for hydrogen is the electron in this position. The ground state for other atoms is just that all the electrons are packed down as low as they can go. And I'll have to show you how we figure that out. Because this orbital only holds 2 electrons. This orbital only holds 6 electrons. And so forth. We'll get to that in a minute. But the ground state for other atoms is lowest possible energy. Right? When we say ground state 1, that's only for hydrogen. Well, and helium, because it only has 2 electrons. So that's the Bohr model. And remember, a model always indicates a theory. Bohr's theory was that this is the way the atom is constructed, and that's why we get those lines, because of the transitions here. So here's a representation of the Bohr model on a graph showing these energy levels. So the first energy level is way down here. The second energy level is quite a jump, but the third, fourth, and fifth, the gaps become closer and closer and closer as you go farther out. We're only showing 3 transitions here to give you light. This one, and this one. There's a 4th one. I'm not sure why they left it off of this one. But for these 3 lines, right, we have a transition. Here's another way of showing it. From 2 to 1, no, there's 1. This is 1. This is 2, 3, 4, and 5. So they left out the nucleus, right? So don't mistake this little circle for a nucleus. This is the first energy level. And the nucleus is down there. It's so small it's invisible. So the transition here they're showing is between 5 and 2, 4 and 2, 3 and 2. Gives you those three lines. Now, we know the wavelengths, right? So if we know the wavelengths, we can calculate the energy of that transition in joules. And this is one formula that gives you that transition. All right, so here's your constant. I'm sure it's got a name, I just don't remember what it was. And this only works for the hydrogen atom. Because if you get more than one electron in there, you also have more than one proton. Then you start getting interactions between the electrons as they transition. So once you get up, in fact, Bohr's model only works for the hydrogen atom. It doesn't work for anything else. It works for hydrogen-like atoms. What do I mean by that? Well, if hydrogen is this, right, with one proton, and helium has 2 protons, lithium has 3 protons, and beryllium has 4 protons, that means we start off with 4 electrons. Excuse me. 1 electron here, 2 electrons, 3, 4. Okay? So what would be a hydrogen-like atom? Well, this one, of course, is like it is, but this one would have to be, we'd have to take away 1 electron. Oops. Take away 1 electron, that leaves us 1 electron. It looks like hydrogen, only it has 2 protons instead of 1. This one we'd have to have a 2+ charge. Get rid of 2 electrons, leaves us 1. It's like hydrogen. And for beryllium, you see where this is going. So you have to ionize them to leave you only 1 electron to deal with. Then you can do the calculations using Bohr's model, because there's only 1 electron left. But the calculation also has to take into account the number of protons. Now, in this one, in this equation, this is for the hydrogen atom only, and it's not for any hydrogen-like atoms, just for the hydrogen atom. And what we need to know is, what is the level that it's finally reached? Right? So if it's going from inner to outer, this would be the bigger number, this would be the smaller number. Say it was, initially it was ground state, 1. Right? So that's -1. 1 squared divided into 1 is 1. And then this one would be whatever maybe the second level. So this would be 1/4. -1 times that value gives us the energy, joules. Okay? If you do it that way, then you have that energy is equal to this value. And then you can calculate, right, because you'll have the energy value there. It's equal to that. These are 2 constants. Then you can calculate what's the wavelength. Right? What should the wavelength be with the transition from 1 to 2? And see if it matches up with the recorded wavelength.
So the initials always want to be 1. Unless
It depends. It depends on whether the electron's going out
or in.
or in.
Okay.
Right? If it's coming in, that'll change the sign.
Okay.
Right? So in that way, you'll know whether the energy is being added to or leaving. So in this case, we're going to take transition from N5 to N2. Right? So this one, it's going from way out to close by.
Yeah.
So from 5 to 2, the final one is 2, the initial one is 5. So this would be 1/4 minus 1/25 times that, and you get this value. And then we take that value and we set it here equal to Oh, well, okay, we're doing two separate calculations. This is the energy we get by that calculation, Bohr's model. And this is the energy we get from the wavelength that should be assigned to the blue light from this one. We find out that they're equal. So what we could have done was take this one and plug it in here, fill in everything with the wavelength, and then calculate the wavelength. Okay, so here's the wavelength. 434 nanometers is 4.34 times 10 to the minus 7th meters. Okay. I didn't show that conversions right there. So that's why I need to explain it. That is derived from that one right there. Using that little trick I showed you earlier. Okay. So the Bohr model for hydrogen, at least, fits. The Bohr model tells us and agrees with the actual measured wavelength for the lines in the hydrogen spectrograph. Okay, so here's another convention. If this is the nucleus, let's say we've got one proton, and we got these orbitals here. And then I said, if the electron is completely separated from the atom, that's at infinity. So we've got an electron from infinity. What is the convention for energy? Well, this energy is taken as 0. That's the 0 point. Infinity is 0. So if the energy decreases as you get closer to the nucleus, it gets more negative, right? You're starting at 0, and the only way it can decrease is to be negative. So the larger negative number for the orbital increases. You get more negative as you get closer to the nucleus. Sometimes that spins students' heads around. I wanted to make that point. That's what this slide is all about. All right. So what we've discovered is Bohr's model is not correct. It's a good start, and it answers some questions. But it only works for hydrogen or hydrogen-like atoms. Now remember that formula with the 1 over n squared and the 1 over n squared. The 1 in each of those positions up there this is initial, this is final. The 1 is equal to the number of protons. Okay? So if you have a hydrogen-like atom with more than one proton, say helium, we're going to say helium plus 1 ion. We're going to use it for our transition. Then you can substitute 2 here for the number of protons. Okay. That's the difference between the earlier calculation and this one. You have the n is equal to the energy level, and the 2 is the number of protons. But remember, that only works if it's hydrogen-like. It's going to be an ion where it's lost all of its electrons but 1. Then the calculation works. So in that respect, the Bohr model works, sort of, if you make those allowances. Right? And that's been proven in the laboratory. So you can take that in the bank. Electrons do not move around in circular orbits. We can't tell where the electron is in its orbit. There's no way. And that relates, let me see. Let me check ahead and see if I'm coming to the right place. We're getting there. I won't say it yet. But these are not correct. Electrons do not move around in a circular orbit. And it's only good for hydrogen or hydrogen-like elements. Okay, so what color of light is emitted when an excited electron and hydrogen atom falls from 5 to 2, 4 to 2, 3 to 2? Well, we can do this qualitatively because we know there are only 4 wavelengths. And we were only given these as our 3 to investigate. This jump from 5 to 2 is going to be higher energy. So it's going to be toward the blue. So that one should be blue. The next one is less energy. So it's going to be headed toward the red. I think it's what, green? Yeah, that one's green. And the last one is red or orange. But the calculations, you can do the calculations. But like if you're in a hurry on a test, that's the way to do it. Just recognize that shorter wavelength means higher energy. And the transition from 5 to 2 is higher energy than 4 to 2 or 3 to 2. So that's how you get them in order. Okay, so that'll have the longest wavelength, the least amount of energy. Now, here's why, and this was proven by Werner Heisenberg, that at this level of investigation, this Heisenberg uncertainty principle is true for all matter. It's just, it becomes more significant as the size of the matter gets smaller. So it really only becomes significant when you get down to the size of an atom, or electron, or proton, in that range. What it says, basically, is that you can't know both the velocity and the position at the same time. Right? If you know the position of your particle, you can't know how fast it's going. Heisenberg called it momentum, right? Which is just mass times velocity. But we're focusing on velocity because as long as we hold the mass constant for the electrons, then we can discuss it in terms of velocity alone. So here's the momentum part, and here's the position part, the uncertainty of a particle's position, like how far is it off of where you think it is. And these multiplied together are always greater than or equal to Planck's constant divided by 4 pi. So you don't have to remember that. I think it should be in the useful information if you need to reference it anyway. Let me just check to be sure. It's not there. The fact that it's not there means that you don't have to know. Okay. Good news. We're just making a point here. When you get down to that size, then this value for that very, very small mass means that you're also limited to the position that you know. So things like human size, you know where I am. Right? There's no uncertainty there, especially if I'm not moving. If I'm moving, that's still not an impediment because my momentum times the uncertainty of my position is always greater than this value. So you can always find me and know how fast I'm going. But if I got really, really, really small, that would be a problem. So this says that Bohr's model is kaput as far as knowing that the electrons move in a circular orbit. We had to find a, we keep his theory, it's valuable in some respects, but we need a new theory to answer some other questions. So that's where, well, first attempt was the wave function. And that led to the quantum mechanics. In quantum mechanics, it's just, we've already talked about quanta. Quantum mechanics just says that the electrons can only be in certain discrete positions, which is still valid for Bohr. But because Heisenberg said we can't know where they are, they could be anywhere in that orbital, right? And the best way to describe an electron in that orbital is not with a particle, but with a wave, right? So electrons are like light. They have that dual nature. They can either be waves or they can be particles. Okay? And the wave nature, as I described earlier, the wave nature of an electron is taken advantage of when we image an object in an electron microscope. But it all has to do with this probability distribution. Since we can't know where the electron is, sometimes you'll see like colored dots around there. It says, this is the most likely place you're going to find the electron for that orbital. We're inching our way toward quantum mechanics. So when you see a depiction of an orbital for an atom, you'll see, say, the nucleus. And that's most likely where you find it, right? Or it might be like this one. That's most likely where you find that electron. It's all probability. And it has to do with this, and it's quantified in a wave function. That's the Greek letter psi. Anybody know fraternities, sororities?
Yeah.
They like to use Greek letters. There's one, several of them have psi in their name. I don't know why. Probably because it's just a cool symbol. It looks like a pitchfork. Okay. So this is one way to represent it as a cloud, right? So that's the 1s wave function. And I'll have to explain what 1s means later. But we'll just focus on this. The distance from the nucleus says that most of the probability, the highest probability of finding that electron is very close to the nucleus. Actually, it should look more like this. If we spread it out, it should be like that and like that, right? Because you're not going to find an electron right at the nucleus. Right? There's going to be some gap between it, and the most probable distance is right there. Okay. Let's see. Well, okay, here we go. That's the correct representation for that particular orbital. And you can do that for any of the orbitals. There are chemists and physicists that just spend their entire careers doing this stuff. So they're the ones you need to talk to if you want a complete understanding, and then maybe not then, right? Because once you develop a language that you use to discuss with your colleagues,
You know, it's like it's a narrow channel and they don't understand what you're saying, right? Most disciplines are like that. Right? When I transitioned from food science to agronomy, soil science, it took me about a year to get comfortable with their lingo. But once I did, you know, it made sense. And then I could talk their language. Okay, and also remember that these orbitals, while we draw them in 2 dimensions, they're actually 3 dimensions. Right? Okay, so here's how we describe an orbital. We use quantum numbers. And this you will need to know. Quantum numbers. And we've already talked about that one. That's the principal quantum number. And that principal quantum number references the size of the orbital and its energy.
Is that a 5 for this?
I'm sorry?
Is that a 5 for this? Right there?
Where? That's an S.
Okay.
Size. So, and it goes in the sequence 1, 2, 3, 4, on up. It starts with 1 and goes up in increments, whole number increments. Let's see, L. L is the next quantum number. This is called the angular momentum. Quantum number. And it refers to the shape of the orbital. Now, is it spherical? Is it shaped like a dumbbell? Or does it have a donut in it? Some are some really weird shapes. This is often called the shell, and this would be the subshell. Your textbook might refer to them that way. That's the only reason I'm putting them there. And this sequence of numbers is n minus 1. And then that's where it starts. So it starts with 0. And it goes in whole number increments. Right? So think of this as we're tunneling down through levels. Or tunneling up through, if that makes sense. We're tunneling through levels. If n is 1, then the angular momentum, the only possibility is 0. Right, because it's n minus 1. If n is 2, then L could be 0 or 1. It could be 2 minus 1 is 1. And it could also include these two. If it's 3, it could include those 3. If it's 4, it could include those. So the highest number possible is n minus 1. Oh, that's a good point. There can be as many L levels as there are number here. So if this is 4, you can have 4 levels. 0, 1, 2, 3. You can have, this is equal to the number of levels. So this would be 3, 2, 1, 0. It's better to go from high down. So if it's 4, you can start with 3, 2, 1, 0. If it's 3, you can go 2, 1, 0. If it's 2, you can go 1, 0. If it's 1, you just got 0. Right? So the number of levels is equal to the n value. Okay, next. Next is m sub L.
This is the magnetic quantum number. And this has to do with orientation, direction. So if you have and this is a sublevel, this is a sublevel of that one, this is sublevels of this one. So each one of these sublevels then can have a certain number of levels at this level. So the orientation says which direction does it point in space. Right? If it's 0, it's spherical. Right? The shape is spherical, so it really doesn't have a direction. If it's 1, it could be 3 different directions. It could be this way, it could be that way. So how do we figure the values here? Well, the possible number of values is derived from the L number. That's why it's M sub L. So if we take 0 there, it can be minus to plus that value with increments of 1. So 0, it can only be 1. 1, it could be minus 1, 0, plus 1. Okay? If it's 2, it can be minus 2, minus 1, 0, plus 1, plus 2. Okay? And you can carry it out to ridiculous. But for example, when I said L equals 1, then the possible orientations could be on the x-axis, on the y-axis, on the z-axis. Right? So you have 3 there. This one could be, it gets really complicated. Some of the x, y, z works, but one of these is like a donut plus some other stuff. So it gets really complicated quick. That's why I don't spend a lot of time on those. Just learn how to use them. And then the last one is S, which is the spin quantum number. So the spin quantum number just means that it can have a possibility, and this is for electron, what would we call it? Well, electron spin. And it can have plus 1/2, minus 1/2. That's it. For any one of these, it can be plus 1/2, minus 1/2. Okay, so there are your 4 quantum numbers and what each one means. Now we need to learn how to use them, because that's the really important part. And once you learn how to use them, then this starts to make sense. Anybody need a break? How are we doing on time? 11 o'clock? We'll go till 12:20. Well, you can get up and go and take a break if you want. It's all recorded anyway. I guess if 3 people leave, we'll pause it. Yeah, go ahead and take a break. And let's. Okay. Pick up where we left off. I have a marker. So we had just finished describing how to, what each of the principal quantum number, momentum quantum number, magnetic quantum number, electron spin quantum number, what each one of those means. Now we can look at how many there actually are of these quantum numbers available for filling orbitals. with electrons. So if we say that N can be anything from 1, 2, 3, 4 on up, and L will have the exact same number of levels as each one of these as it arrives. Remember, these are cumulative. We add them together to build our atom. Then for 1, we can only have 1, that's 0. For n equals 2, we can have 2 levels. That's 1 and 0 for this one. Then for 3, we can have 2, 1, and 0, which is 3 levels within that level. And for 4, we can have 4 levels, 0, 1, 2, and 3. All right, so principal quantum number, angular momentum quantum number, magnetic quantum number. Remember what each one of these stands for. This is the primary energy level. So in the Bohr model of an atom, you calculate the energy of the electron based on this N number. So all the electrons within that energy level have the same energy. For L, that's the angular momentum quantum number, and it describes the shape of the orbital. So for the zeros, and we have letters that we apply to each one of these. The zeros are S, 1s are P, 2s are Ds, 3s are Fs. So for the S orbitals, they're all spherical. Maybe that's where the S came from. The Ps have a different shape. They're more like dumbbells. The Ds and S are really weird, so I'm not even going to talk about them. Then within each one of these, you can have a set of sublevels within each one. Starts with the negative of the number and goes to the positive by increments of 1. So for 0, we can only have a 0. For 1, we can have a -1, a 0, and a +1. Okay? For 2, we can have a -2, -1, 0, +1, +2. Okay? So you get the pattern. For 3, we just start with -3 and work our way up to +3. And remember, for the spin quantum number, it's either +1/2 or -1/2. Okay. Now, knowing that, the number of possible orbitals for the first level is only 1, because it only has this one N number, which means it only has a 0, and the 0 can only have a 0 level. So it only has 1 orbital, period. For 2, we can have a 0 and a 1. So we can have this 1, plus we can have, for this one, we can have 1, 2, 3 orbitals. So you can have 4 total. So here we have 1 and 3. So 4 total at the 2 level. For the 3 level, we can have the 1, the 3s, and then we add another level, the Ds, right, for our L quantum number of -2. So there's 5 more here, so that's 5 plus 3 is 8, and 1 is 9. Just for 3. And for 4, we can have 7 here, so that's 7 plus 5 is 12, and 4 is 16. So that's how many orbitals you can have for each of the principal quantum numbers. But as you build your atom, you're building from here down. So you're going to add in electrons as you need them and add them together. So the total number of orbitals available, if you're at the 1 level, you have 1 orbital with 2 electrons each, like +1/2 and -1/2 spin. For the second level, you have a maximum of 4 times 2 is 8. So 8 plus 2 is 10. And then for the third level, you have a total of 9, so that's 18 at the third level. So when you look at it that way, we go to the third level here, and we say 1, actually, that's the third level. Hold on a second. Let's not go there yet. It would take more explaining and would take us out of sequence. So let's try this example. For the principal quantum number of 3, n equals 3, what are the number of allowed subshells? Different values of L. So L is the next level. Different values of L. So for 3, we can have 0, 1, and 2. So you can have 3 levels there. Okay? And it could be, the 0, of course, will be, this would be S, so it would be 3S. This would be 3P, and this would be 3D. For L equals 2, so let's just take this 1 right here. L equals 2. How many n sub L's can we have? So we start at minus 2, minus 1, 0, plus 1, plus 2. So we can have 5 levels within L equals 2. Okay? Let's see, we're going to get some action out of this one.
An s orbital has a spherical shape with the nucleus at the center.
So s orbitals are all spherical. That is, the probability of finding an electron is within a spherical domain. Yep. Not going to let me use my. Okay, that's fine. All right. So here what we're looking at is the s orbitals are definitely spherical. But when we slice through them to find out what's their fine structure, we find that the 1s orbital is definitely spherical, with probabilities that are distributed within that sphere, but there are no regions in 1s orbitals that have no probability. Whereas when you get to the second level, the 2s orbital is spherical, but there is one section, there's one region in here where the probability of finding an electron is 0. That's called a node. If we look at it on this probability distribution here, we find that there's your node, and then you have this distribution out here. So for 3s, we have 2 nodes. So you take the principal quantum number, subtract 1, and that's how many nodes you have within the s orbitals.
The 2px orbital is in the shape of a figure 8 along the x-axis. The 2py orbital is in the shape of a figure 8 along the y-axis. The 2py orbital The 2pz orbital is in the shape of a figure 8 along the z-axis.
All right, so the p orbitals, where L equals 1, right? L equals 0 is S, L equals 1 is P. We have sometimes designated as PX, PY, and PZ for the different directions that the orbitals can go. Remember, these are N sub L levels. This is the shape, and which is dumbbell for the ones, and the N sub L is direction, orientation in space. So this is along the x-axis, this is along the y, and this is along the z. And this is another way of looking at them. The d orbitals are a little more complicated. Remember, we have 5 possibilities for those.
The 3dx squared y squared orbital has a cloverleaf shape that lies in the xy plane and is aligned along the x and y axes. The 3dxy orbital has a cloverleaf shape that lies in the xy plane and bisects the x and y axes.
The 3dxz orbital has a cloverleaf shape that lies in the xz plane and bisects the x and the z axes.
And then one more, which is the weirdest of all.
The 3dz2 orbital is shaped like a pz orbital with a donut of electron density around the center. It is aligned with the z-axis.
Actually, I skipped one, didn't I? Yeah.
The 3dyz orbital has a cloverleaf shape that lies in the yz plane and bisects the y and z axes.
So there are the 5 possibilities for the d orbital, with sublevels of -2, -1, 0, +1, and +2. So there they are in a different representation. These are the f orbitals. So there can be 7 possibilities there, and it just gets weirder and weirder. So we're not going to spend any time on those. Now we come to the M sub S, electron spin. Electron spin can either be +0.5 or -0.5. So once you get down to this level, then within each one of these, you can have 2 electrons. But those 2 electrons have to have opposite spins, which means one electron will be +1/2 and the other electron will be -1/2. If there are 2 in there together, otherwise you just pick +1/2 as the spin quantum number for that one electron. But if you put them both together, they have to have opposite spins. And this brings us to the Pauli exclusion principle. Pauli said, very simply, that of the 4 quantum numbers, no 2 electrons in an atom can have the same set of 4 quantum numbers. So let's say, take an example. They can have the same principal quantum number. They can have the same angular momentum quantum number, which, well, let's just keep it at 1, right? And they can have the same magnetic quantum number. Let's make it, let's see, 0. Right? So 2, 1, 0. Then one of the electrons can have this one, and the other one would have to have a -1/2 spin. So that way, you have unique sets of quantum numbers. Every electron has its own unique set of quantum numbers. Pauli says that has to be obeyed. You cannot break that rule. Now, comparing 2 other electrons, they could have completely different numbers up here. But they're always different sets of 4 numbers to describe an electron. So each electron has its own unique set of numbers. So what's a polyelectronic atom? Well, it's anything that's not hydrogen, or anything that's not hydrogen-like. That is, It's not some other element where all the electrons have been removed except for one. That makes it hydrogen-like. And those electronic atoms tend to create real problems because electrons repel one another. And that tends to shift the energy distributions of the orbitals. So things get really complicated really fast. Okay. So here are the orbital energies of hydrogen, where you have 1s is the lowest energy, 2s and 2p's. Remember, these are all the same energy level. 3, 4. Except when you start putting in more electrons. Then these energy levels shift. So technically speaking, the Bohr atom only works for single electron atoms. Then you can say that each principal quantum number defines the energy for that level. And every electron in there has the same energy. But when you put more than one electron together, you start shifting those levels, and these sublevels tend to shift their energies. So let's see what they have to say about it.
In a hydrogen atom, all subshells for each N are at the same energy. For multi-electron atoms, the subshells are spread apart due to interactions between electrons.
So there you saw a shift in energies simply because we add more electrons into the atom. Oops, too far. Now, what do we mean by the penetration effect? The penetration effect refers to the probability of finding electrons, or the distribution of electron density in these orbitals. If you compare, well, in this case, if you compare the 2s electron and the 2p electron in their orbitals, then you find that the 2s, remember the 2s has a node. So its main peak, this is energy, is going to be, and this is distance. Its main peak is going to be out here somewhere. But here's the node, that's 0. Here's the node, and you get some distribution of electrons closer to the nucleus. Whereas, and this is 2s, 2p is going to be, well, we've got a drawing here. There we go. 2p is going to be more like this. So the fact that S has a penetrating effect with density down here gives it overall a lower energy level. So the S is still lower than the P on average. That's called penetration. If we look at a 3s orbital, it's going to have penetration with 2 nodes. And here we look at the 3s. Here's the 3s, the red line, it goes up there like that with these 2 nodes. The 3p has 1 node right here with penetration. And the 3d is here with no nodes. Okay, all of that is penetration. Now let's get to the periodic table. All of this that we've been talking about up to this point has been to set up the description of the periodic table in its present form. But we need a little history first. Back in the late 18th century, scientists were noticing similarities among the different elements. They knew how to isolate some of the elements, and then they could characterize how they behaved, both physically and chemically. Dobereiner was one of the first to recognize these similarities, and he set up tables of triads, where he had 3 elements that behaved similarly. Now, these three can't be similar in physical properties because chlorine's a gas, bromine's a liquid, and iodine's a solid. But their chemical behaviors were very similar. They're all halogens that we know now to be part of the table in this region. They're grouped vertically. Those were Dobereiner's triads. Then a little bit later, Lothar Meyer and Mendeleev noticed larger groupings of elements that had similar behaviors, both physical and chemical. And they grouped them together. I think at that time they called them families. Now, the reason that Lothar Meyer does not get credit for the current arrangement of the periodic table is because he didn't go the extra step that Mendeleev did. What Mendeleev did was, and at that time, remember, all the elements were known only by their weights, their relative weights to one another. So they didn't know about atomic numbers yet. So Mendeleev took all these elements that were known and grouped them into families. And progressively, from weight to weight, higher and higher weights. And he noticed that at some point, as we're adding them in, we spill off the edge and say, wait a minute, this element is just like that one over there. So he turned around and put it over here. That's why it's called a period. Because with one period, you go back to the same characteristics in the next period. And they overlap. So Mendeleev did that. And the other thing he did was, when he found a place where there was supposed to be a member of that family at that given weight, there was no element there. No one had found it. So he left it open. And he said, all right, someday somebody's going to find an element in that spot with approximately this weight and these physical and chemical characteristics. Sure enough, they did. They filled in those spots with elements that Mendeleev had identified. Also, what he did was, occasionally you come along and you find that the weight, the order of weights, did not allow the matching up of families. So he rather than be hard-nosed about it and stick to the weights, he just flipped it and put the lighter one on the heavier side so that they would line up with their families. And it turns out that that was true also. So his predictive capability, the ability of his periodic table to predict the existence of new elements is what won him the notoriety. He's given credit for the periodic table. All right, so when we're building an atom, each time we move one to the right, we add another proton. So for a neutral atom, that means we add another electron too. So you have to know, where do we put those electrons? Well, there's an order that they go into an atom. As you build the atom, one proton at a time, one electron along with it, then it's known as the Outfile Principle. And that's just German for, this is how you do it. Since I don't know German, don't hold me to that. So in this case, this just shows that we fill oxygen in this order, and this is our shorthand. So there's oxygen with 8 electrons, and we start at the lower end, principal quantum number. Remember, we can only have one orbital, one L for the principal level 1, but at the second level, we can have an S, and we can have P's. Right? We can have one of these, and 3 of these. Okay? So we just need to find a place for all of our electrons, and we start at the low energy first, work our way up. So we know that only 2 can go in there because it's a single orbital, with a plus half spin and a minus half spin for those two electrons. Like that is the way we write it. Same thing for the 2s orbital. Okay, so we've used 4 of them. Now we need to put 4 in here. Right? So we put 1, 2, 3, 4. Notice I put 3 up spins before I put the 4th one down. That's known as Hund's Rule. I think that's on the next slide. And that means we have 4 in here. So 4, 5, 6, 7, 8. We found places for all of our electrons by the Outfile Principle. And there's Hund's Rule. It just says that in these sublevels, you put an up in every one before you can put a down, in other words. So you put a plus half spin all the way across until you fill up, and then you need more room, then you come back and put a down spin or a minus half spin for the rest of it. Your book might do it this way. These slides are like this with boxes. I prefer it's much quicker to just put a line for each of the suborbitals and then up and down arrows. It works a lot quicker. And that's what's known as the electronic configuration of the atom, or an orbital diagram. Now, what do you do if your atom is charged? Right? So we've already learned that the preferred charge for oxygen is 2 minus, isn't it? Right? So that means 8 electrons neutral plus 2 more is 10 electrons. So we've got 2, 4, 6, 8 in there already. These other 2 electrons go there and there. Okay? So this is a condition that we know as filled orbitals. And it's very preferable for an atom to have filled orbitals when it can get them. That's why the charge on oxygen is 2 minus, because we filled every space out to this place. And the next one, the next energy level, is the next quantum number up, right? So it prefers to stop right there. Notice also that with those 2 extra electrons, we've moved to the neon level. So this is also the electronic configuration for neon with 10 electrons. And that's why we say that these elements, when they react, they're trying to look like noble gases, because the noble gases have filled orbitals all the way out to the end of their energy level. Okay, so what do we mean by valence electrons? There are a couple of definitions. One, a valence electron is an electron that's available for bonding. Right? But it's available for bonding for one reason. These are the electrons in the highest principal energy level, quantum number. So for our oxygen, we have 2 plus 6 is 8 valence electrons. So all you have to do is find the principal quantum number, count up every electron in that principal quantum number, and you have your valence electrons. Now, the periodic table is organized based upon the way that electrons are filled in the orbitals. So we find that these first 2 are filled s orbitals, right? This s orbital has only 1 electron in it. The s orbital for these elements have 2 electrons in them. These are all p orbitals. So we fill the p's. Remember, we have a px, a py, pz, with 2 electrons each, maximum, right? So that's 6 possibilities. 1, 2, 3, 4, 5, 6, and they're filled. The d orbitals have what? Well, d is 2 L equals 2 for D, which means -2, -1, 0, +1, +2. 5 possible orbitals with 2 electrons each, so that's 10, right? It can accommodate 10 electrons. So in this section, transition metals, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And those d orbitals are filled. For the F's, right, we have -3 up to a +3. So that's 7 times 2 is 14. So 14 possibles, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That's why there are that many elements possible in each one of those sets. Well, that's why the periodic table is arranged the way it is. And knowing that information, you can write the electronic configuration using this chart, or you can use the next one that I'm going to show you. So if we have our principal quantum numbers here, 6, 7, so these are all n's. And then we have our L quantum numbers, right? So for this one, it's only 1s. For this one, it's 2s and 2p. 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, and we'll just put 5f out here, okay? And then we have 6s, 6p, 6d, and 7s, 7p, and that should cover all of our elements. So what you do is know what order you fill the elements. You start here and go diagonal down to the next level, like this. Okay, this one, this one. Just keep drawing your diagonals. And that shows you the order in which you fill your electrons in the available orbitals. Notice here, in the beginning, it starts off in logical order. 1, 2s, 2p, 3s, 3p. But then it skips the 3d and goes to 4s first. Then it goes back to 3d. Right? So that's the first place that it happens, at inversion of order. That one's getting weak. Let me find another one. Let's try green. So if we were to write out an electronic configuration without an element first, oops, it'd be like that. And that would be the order that you fill them. Okay? So what I would do is memorize that table just the way I built it here. And when you walk in for your exam, first thing you do is flip the paper over and write that thing down before you do anything else. Then you go start looking at questions. Okay, let's do some electronic configurations based on this principle. Okay, for sulfur, that's not going to show up very well. Let's see if I can find something darker. Red. Let me see if red shows up. Yeah, that's good. So sulfur is how many electrons? Well, the same number as protons, 16. So we have 16 protons, 16 electrons. So we have 1s, 2s, 2p, 3s. If we need more, we know where to get them. So this is 2, plus 2 is 4, plus 6 is 10, plus 2 is 12, right? Now we need another 4s, 2. Let's see, 2, 4, 10, 12, 14. Oh, that's not right. That's not right. 3s, 3p, 4s, d. That should be 3p4. 2, 4, 6, 3s. Oh, 3p. All right, let that one out. 3p, 4. 2, 4, 10, 4, 16. This one's not working very well either. Ah, it's a brown. Okay, so that's sulfur. Another way to write it, shorthand, is to start with the element and work your way back to the next period. And we find that the very last time you crossed the path of a noble gas was neon. Neon has 10. So we're going to use neon as our core, and then we're going to move to, let's see, 2, 4, 10. So then we start with this one. And that's the shorthand way of writing the sulfur. How about barium? We're definitely going to need a shorthand for barium because it has 56. Okay? We could write the whole thing out, but we'd rather use a shorthand. So the next one was xenon, 54. So if we start with xenon, then what do we put out there?
Well, use the periodic table, and I'll show you how.
With xenon, then you move to the next one, and which orbiters are filling here? Well, 1, 2, 3, 4, 5, 6s. 6s is the next orbital filling. With 2 electrons, 54 plus 2 is 56. So barium can be written with xenon at the core and 6s with 2 electrons. These are your valences. This is the valence electrons, And these are your core electrons here. Okay? This is core, and these are valence. Now, europium is a special case because europium is way down here, and europium requires the filling of f orbitals. So, if we go back following europium here, it fits in right there. Then we have to go back here and pick up xenon again. So europium is 63. And we're going back to xenon at 54. Okay? And xenon is then going to fill 6s2. And then, let's see, 6s2, and then we go back up here to 4f. And 4f is filled 1, 2, 3, 4, 5, 6, 7. We have to count lanthanum, right? Because we can't go anywhere past this one. Lanthanum is here. So 1, 2, 3, 4, 5, 6, 7. And 7 electrons here is 9 plus 54 is 63. So that's the electronic configuration of europium. And I'm not going to hold you to the f orbital elements because they get really, really weird. Once you start getting that many protons and electrons in there, then the energy levels really do some flip-flopping. So that's just to illustrate the point. If you can do something like barium, I'll be satisfied. Okay. Now for periodic trends. The periodic table is set up so that we can identify certain types of trends. And one of these three are the ones we're going to focus on. There are many others. These are the most useful at this point in your chemical education. Let's see, let me see if black's ready to go again. Ionization energy, electron affinity, and atomic radius. Atomic radius is just the distance from the outer electron probability position to the center of the nucleus. And it varies depending on who you talk to and who did the calculations and the experiments to determine it. But if you use the same person and their data, then you'll see the trends. You just don't want to mix sources. But ionization energy and electron affinity are both quantified values in terms of joules per mole. So we're going to define ionization energy okay. I think what I'm going to do is pause the video and go get a marker that works. So next time you see me, I'll have a black marker that works. Okay, I'm back with a better marker. Ionization energy. All right. All right, what's the definition of ionization energy? It's the amount of energy that's required for this process to proceed. This is our generic element, right? There's no element on the periodic table with just an X, so we'll use X as a stand-in. This element needs to be in the gas phase. Why? Because when we add energy to do this, and eject one electron, when we add enough energy to do that, we don't want to be adding energy to change a solid to a liquid and liquid to a gas. We start in the gas phase. Then the energy that we use is only used for one thing, to eject the electron. Right? So this is going to be in some value of joules, and usually joules per mole. Okay. Let me just go ahead and define the other one as well. So what's electron affinity? Electron affinity is similar, but not exactly, we don't mean going backwards. In other words, that's not electron affinity. Electron affinity is you start with the neutral atom also on this side in the gas phase, right? And in this case, you measure how much energy is released when one electron is added to that neutral atom, which gives it a negative charge, and there's a certain amount of energy associated with that. More than likely, it's a negative energy because it's being given up. Remember, as electrons approach from infinity, infinity is zero energy. And as you approach, the energy gets less and less and less relative to the atom. So where does that energy go? Out. And that's what this measures. Okay, atomic radius, we'll get to that. But these two are defined similarly because we start with a neutral atom in the gas phase. In this one, we eject an electron. In this one, we add an electron and measure the amount of energy in either one. Okay, so now let's go back to ionization energy and dig into that one in more detail. Okay, there we have the formula. And notice that for a magnesium, for one electron to be ejected, we have to add 735 kilojoules per mole. Right? So per mole of magnesium atoms, we have to add that much energy. Right? So that's the first ionization energy, when you start with a neutral atom. But you can also write this equation for the second ionization energy. So you start with the singly charged, and now you get to the double charged because there's another electron being removed, and you get another delta H. That's first, that's second energy. Well, they're using I for ionization energy. What you want to note here is that the second ionization energy is higher than the first. And there's a simple explanation. Once you've got a positive charge here, removing a second electron, which is being drawn by that positive charge, is much more difficult. It takes more energy to remove that second electron because you're removing it from that pre-existing ion. Now, notice what's happening. With magnesium, if you remove an electron, you get the electronic configuration of sodium, right? Because you've removed an electron. If you remove the second electron, what does it look like now? It looks like neon. So you remove 2 electrons from magnesium, which has 12 to begin with, and this one only has 10 electrons, and they look like neon. Now what are you doing? Well, if we look at the electronic configuration of magnesium, which is 12 here, right? So we start off here at 1s2, 2s2, 2p6, 3s2, 2, 4, 10, 12, okay? Then if we get down to this one, we're at 1s2, 2s2, 2p6. These are our valence electrons. These are our core electrons. So once you get to that point, when you try to remove a core electron, it takes much, much, much more energy. And here it's proof. We go from 7 to 1400 to 7,000 kilojoules to get the first core electron. All right? All right, what are the trends on the periodic table? Well, we can look at it in a period or in a family, right? And we're gonna discuss the trend in terms of the first ionization energy. Right? You can talk about it in terms of other ionization energies, but we don't have time or the need to talk about second and third ionization energies as a trend in the table. So in a period, the ionization energy increases from left to right. So the first ionization energy increases, let's look up here. As you go from sodium, magnesium, aluminum, silicon, phosphorus, all the way over, the first ionization increases. And the reason for that is you're adding protons. You're adding protons which draw more strongly on the electrons. And since all the electrons are being added to the same principal quantum level, right? This would be 3, n equals 3. You're adding electrons in that same level. Then the ones before it have a tendency to shield the later electrons from the protons. It's kind of like these lower level electrons closer to the nucleus tend to suck up some of the positive charge. So that the outer electrons don't feel that positive charge as much. But still, they do not completely shield. So there's still some positive effect from adding protons, and that causes the first ionization energy to increase as we move to the right. Now, what about in families? Well, in families, if you go down, what are you adding? Principal quantum levels, right? Which means that the electrons are being added way, way out here, the further down you go. The further away from the nucleus, the less they feel the nuclear charge, plus the outer energy levels are in a position, it takes less energy to go to infinity here than it does to go to infinity here, right? So these take less energy. So as you go down a family, you get less energy, or as you start from the bottom and go up, it takes more ionization energy. So when we combine those two, more energy this direction and that direction, then from lower left to upper right, you increase the amount of ionization energy required. Okay? That's true. I already told you that. And here are our trends, right? So here are within the periods, and as you go from left to right, right, discounting hydrogen, of course, you go from helium, and then you go, well, let's start at lithium. Lithium's over here in this period. The first period is a little squirrely. So if you go from lithium, you work your way up in a general trend through the elements in that period to neon and as a maximum. And then you start from bottom here and you work at maximum, start bottom here, maximum, maximum, maximum. Like I said, these are general trends. There are points along those trends where the change flips. And I'll show you a couple of those once we get to it. Well, this is a good place to start. So why did we not see a linear change? Right? For instance, here, beryllium, boron. See, it reversed its direction. Lithium, beryllium, and back down to boron. And then up here to nitrogen, back down to oxygen. Okay? The primary reason is electron repulsion. So what you have is, as you go from lithium to beryllium, the ionization energy increases, and then here it drops back down. Why? Because electrons are going into a different suborbital. Whereas when you get to this one, where you go from nitrogen to oxygen, that takes a little more explaining. So let's say nitrogen is 7, oxygen is 8. So nitrogen is 1s2, 2s2, 2p3, right? We got that. Okay. And oxygen is 1s2, 2s2, 2p4. There, and then the fourth one goes in there. These two electrons, even though they have opposite spins, are trying to occupy the same sublevel. So the repulsion here is much greater than it is for these here. Right? So what happens is, this is the first electron that's going to be kicked out. And because of the repulsion against that electron, it takes much less energy to kick that first one out for oxygen than it does to kick that one out for nitrogen. So that's why the trend for nitrogen-oxygen is reversed. Okay, let's see if we can use the trends to predict. Which atom would require more energy to remove an electron and why? More energy for sodium or more energy for chlorine? Well, let's look and see. Chlorine and sodium are both in the same period. So if we work our way across, we get increasing ionization energy all the way over here. Chlorine then takes more energy to bump that first electron. Lithium and cesium are in the same group, lithium and cesium. So the trend here is it takes more energy as you go up, because the electron is getting closer to the nucleus. And it's at a lower energy level to begin with, which means it takes more to get it to infinity. How about second ionization energies? Which one of these has the larger second ionization energy? Well, let's look at lithium, which is 1s2, 2s1, and beryllium, 1s2, 2s2. Right? They're right next door to each other. So first ionization energy, we kick first one off here, and what does that give us? Well, it gives us that one plus that one. This one gets rid of that one, and now we're into the core. So the second ionization energy for lithium should be higher than the second for beryllium, because beryllium still has one valence electron available. Right? And that, in fact, is the case. And here's what they look like. Several examples. Sodium, magnesium, aluminum. Sodium, magnesium, aluminum. Silicon, phosphorus, sulfur, chlorine, and argon. All in the third period. Right? So if we go across the period, we find that you have to get down into the core. For sodium, you only have to kick the first one out, so the second ionization energy is in the core. Magnesium is the third. Aluminum, you're down to the fourth ionization energy to get into the core. Right. So that's where you get the really big jump, is when you make it to the core. And of course, argon is all core to begin with. Argon has no valence electrons. Now, that may seem contrary to the definition, right? They're all the same energy level, so you would think argon has 8 valence electrons. Well, the problem is, well, I guess you could say that. Argon has 8 valence electrons. The problem is, they're all in filled shells, and argon doesn't want to give them up. So even though, by definition, they are valence electrons, they don't bond. Okay, electron affinity. So there's our definition again. When we add an electron to a gas state neutral atom, we get the singly charged anion, and there's a certain amount of energy associated with that. Now, what does that mean? Well, if you're going to bring an electron from way out here into the first available level, right? Say these are all occupied. So you've got a position here where that electron can go. So when it goes from infinity to that level, where does that energy go? We can't create energy, we can't destroy energy. So the energy that it had, difference between infinity and this level, has to be released. Maybe as light, or maybe just as heat. But there's a certain amount of energy that comes out of that transition. And remember, when the energy is leaving the system, it's positive. So let's look at the trend. As we go from left to right, electron affinities become more negative. All right. That's a bad example. If this is infinity, it's zero energy. And these become negative, negative, negative. More negative as you get toward that. So what we're saying is that the more negative, the stronger the affinity. Right? More negative equals stronger affinity. Okay? So that's what they mean here when they go from left to right. The electron affinities become more negative. So that means the electron affinities are stronger as you go from left to right. And the strongest would be all the way over to the noble gas. Well, actually, we have to exclude the noble gases from this trend because they've already got all the electrons they want. They don't want any more, right? But the halogens, they do want electrons very badly. How about electron affinities for groups? Well, electron affinities increase as you go up. So the strongest affinity for electrons is at the top of the list. So here again, the strength of affinity, in other words, the more negative the number, the strength of affinity is lower left to upper right. Same trend as ionization energy. Now, atomic radius is a little easier to deal with. What are the trends? As you go from left to right, remember we talked about effective nuclear charge. That is some shielding, but still increasing nuclear charge from left to right. So that means as we go from left to right, there's a stronger pull on electrons. And actually, there's a stronger pull on the energy levels. And the electrons just go where they are supposed to. So from left to right, the atom shrinks, gets a smaller radius. How about up and down? Up and down, we're going from principal quantum level 1, 2, 3, 4, 5. Going this direction, we're putting electrons into higher orbitals, which means a bigger atom. So we have a decrease in size from bottom to top and from left to right. So it's an opposite trend to the former two. So they get bigger, the radii get bigger as you go from upper right to lower left. And that was just an example. This shows you the s orbital filling and the p orbital filling, and we leave out the d orbitals and the f orbitals because they don't behave quite as nicely. The atomic radii have been determined for those elements, but they don't fit the trend very well. They have lots of exceptions and reversals. Which is the largest of these, sodium or chlorine? Well, look where they are. Chlorine's there, sodium is here. Remember, they get smaller as we go to the right. So sodium should be the smallest, chlorine should be the largest. Which one would be the largest? Sodium should be the largest, chlorine's the smallest. Because as we go from left to right, we're shrinking the atom. Let me say that again. Left to right in a period, the radius decreases. So the larger atom in these two pair, sodium would be the larger of the two. Lithium and cesium, again, smaller at the top, larger at the bottom because we're adding electrons to higher quantum levels. So cesium would be the smallest, cesium would be the largest, lithium would be the smallest. Okay. How did I miss this? Oh, we never got to that one. When the class was all here, we had to stop. So let me finish this out. So which is larger, the hydrogen 1s orbital or the lithium 1s orbital? Hydrogen or lithium. Lithium has 3 protons. So we both got a 1s here. So which one's going to be a smaller orbital? Which one's going to be the largest one? Look at what happens. You've got 3 more protons here pulling on the same energy level. This one should be smaller. And hydrogen should be larger for that reason. Which is lower energy. All right, this depends on how close it is to the nucleus. The closer to the nucleus, the lower the energy. So if this is the larger one, this is the smaller one, this should be the lower energy. Lower energy, larger radius. Okay? That's what we mean by lower energy. Closer to the nucleus is lower energy.
At room temperature, the metallic element molybdenum exists as a solid crystal. Metallic crystals behave like a 3-dimensional array of cations surrounded by a sea of electrons. A molybdenum crystal can be used to estimate the atomic radius of molybdenum atoms. The distance between nuclear centers in molybdenum is 278 picometers. So the atom radius is estimated to be 139 picometers.
Okay, you may have noticed from that drawing, or that graphic, let's see if I can move it out.
At room temperature, the metallic element of cations surrounded by a sea of electrons.
There we go. Notice that there's a gap in here, right? So if we take half of 278 as 139, what are we doing with that space in between? Because that's real. There is space there. So this is, at best, an estimate. I just wanted to drive that point home.
At room temperature, the halogen element chlorine exists in the gas phase. Gas phase molecules are relatively far apart, since gases have low densities. Molecules move in straight lines until they collide with container walls or other molecules. The diatomic chlorine molecule can be used to estimate the atomic radius of chlorine atoms. The distance between nuclear centers in chlorine is 199 picometers, so the atom radius is estimated to be 100 picometers.
Now in that case, Notice that the centers of the atoms,
The halogen element chlorine exists in the gas phase. Gas phase molecules are relatively far apart since gases have low densities. Name the atomic radius of chlorine.
there you go. So in this case, it's just the opposite. You've got these two chlorine atoms that are really closer together than their radius would imply. So if we calculate half of 199 between the nuclei, we're actually underestimating radius, right? So that just illustrates that, well, first of all, how did they figure that one out, right? Who knows? But there is potential for error there for that reason, and conversely to the determination of the atomic radius of molybdenum in its crystal structure. Oops, I got to take control again. Here we go. So let's see if we can arrange these elements: oxygen, fluorine, sulfur. Oxygen, fluorine, and sulfur in order of increasing ionization energy. So here's oxygen, there's fluorine, and there's sulfur. So if we take our trend lower left to upper right, we should have ionization energy low, next high, highest. Sulfur, oxygen, fluorine, did it say according to increasing, okay? Sulfur, oops, is less than oxygen, which is less than fluorine. So it should be in that order. Atomic size. So how does atomic size fit into this? Lower left to upper right is decreasing size. So increasing size would be just the opposite of ionization. So it would be fluorine, oxygen, sulfur. Increasing size, like that. Okay. Let's see if these final thoughts are worth pondering. Periodic table. The number and type of valence electrons that primarily determine the atom's chemistry. That's true. I've been saying that since the beginning. These valence electrons, the ones in the outermost shells, the ones that are encountered by other atoms as they approach. They see those first electrons. Those valence electrons are the ones that are available for bonding, and they determine the element's chemistry. So Mendeleev was right. He just didn't know why. These elements are similar because they have the same number of electrons in their valence shells, the outermost shells. That's why they behave similarly. Electron configurations can be determined from the organization of the periodic table. Absolutely. If you know the structure of the periodic table, you can get pretty close to the electronic configuration. Let's take one simple like titanium 22. And we're going to do the complete structure. It has to be consistent here. It should be like that. Okay. So titanium, we're going to start with 1s, 2s, 2p, 3s, 3p, 4s, 3d. Right? Remember the Outfile Principle. When we get to that point, we have to do 4s before we get to 3d. And the periodic table confirms. Right? 1s is hydrogen and helium. 2s is lithium beryllium. 2p is boron through neon. 3s is sodium magnesium. 3p is aluminum through argon. And then potassium and calcium are 4s. And then we're down to 3d. Right? So this may be the fourth period, but we use the third principal quantum number for this group. So 3D, 1, 2. 3D, 2. That's 2, 4, 10, 18, 20, 22. So if you know the periodic table structure, you can draw the electronic configuration. That's longhand. Now, if we're going to use shorthand, we say, start with argon. Argon 18. Right? So 2, 4, 10, 12, 18. That's argon, and then what's left over, 4s2, 3d2. Okay? All right, third point. Certain groups in the periodic table have special names. Well, yeah, that's true. We didn't name them earlier. I think we did early on in the semester when I gave you that extra credit where you could draw the periodic table and name the groups. Right? These are the noble gases. These are the halogens. These are the chalcogens, the oxygen group. These are the pnictogens, starts with a P. Right there. That one doesn't have a special name, neither does that one. Carbon group, boron group. Then we have alkali metals, first group. Second to the, on the left, is alkaline earths, or alkaline earth metals. Either one is proper. So there are our names. Notice that some periodic tables have these 1As, 1A, 2A, 3, 4, 5, 6, 7, 8A. Those are archaic. They're not used anymore, usually. Now we just number from left to right, 1 through 18. But these do have some value. Because especially when you're dealing with this level, the valence electrons you have are 1 for 1A, 2 for 2A, 3 for 3A, 4, 5, 6, 7, 8. And that goes back to what we've come to know as the Octet Rule. In other words, when an atom is, or an element is reacting, it tries to obtain an octet in its outermost shell. If we're at fluorine, it would prefer to just add 1 electron and make it look like neon. But if we were at sodium, it would prefer just to lose 1 electron. After all, its electron affinity is very low, so it would lose that electron and look like neon. And where would that electron go? Well, if it was sodium and fluorine reacting, it would go to the fluorine. And they would both look like neon, electronically speaking. That's what would drive the reaction. All right, the basic divisions. Remember, metals down here, non-metals up here. And here's that line there that divides the two. Now, of course, it's not a clear distinction. This is just to help us organize the chart. These are non-metals, these are metals. But when you get close to that line, you enter the realm of metalloids. Sometimes they behave like metals and sometimes they behave like non-metals. And these are the basis for our semiconductor industries. Computers, cell phones, what have you. Because they can go both ways. Oh, I left out the lanthanides, right? So these are all lanthanides because the first member of their group is lanthanum. These are the actinides because actinium is the first group of, the first member of their group. Okay, now we're getting into specifics of the groups, and I'm not going to dwell on that because that would take forever. In fact, I had an entire semester course, nothing but that study.
Right, so we really don't have time to deal with it. If you're comfortable with electronic configurations and the structure of the periodic table, then you'll be in good shape for any exam I might throw at you. And that's it.